Hello, Knights. Welcome to your third lesson on algebra. Today we are talking about something called multiple representation of algebraic expressions. So we're going to start off with something that looks maybe a little bit different from what we have been doing, and then we're going to see how it connects with some of the ways that we have already learned. So algebraic expressions, we've already looked at them before. We're hopefully getting pretty familiar with them, and today we're going to do a couple more exercises that will make them make even more sense. So, where it says engage, draw what shape you would predict for shape 4, 5, and 6 would look like. So I want you to go ahead and pause the video for a second and make a quick sketch. What do you think it would look like for shape 1, 2, and 3 to be continued to become shape 4, 5, and 6? And then whenever you're ready to check your drawings, go ahead and resume the video. Alright, so what I noticed with shape 1 is that there are 2 squares. For shape 2, I noticed that there are 4 squares. And for shape 3, there are 6. And just FYI, I am doing this without a stylus, so I may be resorting to some text boxes later because it's kind of hard to write sentences with this thing. So later on, if I use a text box, bear with me. Hopefully I'll get a stylus in the future. Anyway, so shape 1 has 2 squares, then there's 4 squares, and there's 6 squares. Hopefully we notice pretty quickly that there's a pattern involved here, and that pattern is each time the shape is adding on 2 more squares. So for shape 4, there would be 8 of them. For shape 5, there would be 10 of them. And for shape 6, there would be 12. Like so. So there's actually another deeper pattern that I think that we can pull out from this, other than each time I'm adding on 2. If I'm adding 2 over and over and over again, that actually represents something kind of different. Adding the same thing over and over again, repeated addition, is actually multiplication. So what I'm going to say for question number 1, what pattern do you notice in the drawings? I'm going to not say, I notice that each time I'm adding 2. I'm going to say something closer to like, well, each time, what was happening to the shape number? Whenever I look up here, erase that. How was I going from shape to number of boxes, shape to number of boxes, shape to number of boxes? I have 2 options. To go from 1 to 2 is either 1 plus 1 or 1 times 2. Times 2 makes the most sense here. 2 times 2 gives me 4. 3 times 2 gives me 6. So I'm actually not just adding 2, I am multiplying the shape number by 2. So for my text, I am multiplying each shape number by 2. Come on, there it goes. So what is the pattern? I'm multiplying each shape number by 2. Then I go back to completing the table. So shape number 1 had 2 boxes. Oh no, it's red. Shape number 1 had 2 boxes. Shape number 2 had 4. Shape number 3 had 6. Then we had 8, 10, and 12. Now be careful, just because it goes up by 2 doesn't mean the next one's always going to be plus 2. It means whatever it is actually being multiplied times 2. Times 2. There we go. Alright, question number 3. How many boxes would you predict the 12th shape to have? Well, if I were to extend this ratio table over and put 12 on top, we've already discussed to get the number of boxes, I multiply the shape number by 2. So I would predict that there would be 24 boxes. 24, come on, you can do it. There we go, 24 boxes. Alright, moving on. Write a sentence that describes how you can find the number of boxes any shape would have. Alright, I'm going to go back to my handy dandy text box here because it's probably going to be too hard to write with my hand. So how am I finding any number of boxes here? To find any number of boxes, comma, and then I asked myself, what was I doing each time? I took the shape number and I was multiplying by 2. So I multiply the shape by 2. Great. Hopefully these sentences are getting easier for us to do because they're generally following a pattern. Question number 5. Write an algebraic expression that you can use to find the number of boxes for any number shape. Okay, a lot of us still have some issues trying to remember what exactly this is. So I'm going to write a little reminder to us of what an expression is and what should be inside of it. So expressions have 3 things. Can you remember what those 3 things are? What's one of those 3 things? You're right, they need a variable. What else? Oh my gosh, you're so right. They also need numbers. There's one other thing that they need. Oh yeah, an operation, like multiplying or dividing or adding or subtracting, those things. So, whenever I make my expression, it needs those 3 things: a variable, a number, an operation. In this case, what variable am I given? I am not given one, so I need to declare one. I need to write it out. For shape, what letter makes the most sense? I'm going to go with shape is equal to the letter S. Keep things simple. So far, I have my variable. What is my number that I need? Let me check off my variable. Check. I also need a number, so I have S, and each time I was multiplying by 2, so 2 with a multiplication symbol between them. Is this the best way to write this? No, technically the best way would be 2 first with S behind it, because this is the way that it will always look in our algebra classes. Alright, so key point number 1. There are many different ways to represent an algebraic expression. Today we will focus on number 1, pictures and diagrams, number 2, tables, number 3, verbal descriptions, and number 4, expressions. So if you're questioning what some of these are, I mean, pictures we should know. Pictures are like, all right, one person has 4 cookies. And then we draw a person who's got 4 cookies. A table would be something that's like, here's hours, and here's money. In 1 hour, they made $6. In 2 hours, they made $12. In 5 hours, they made $30. All right, a table is just like a set of numbers where one of them is 1 unit and the other side is another unit. This next one, verbal description, this one's a little bit trickier. Verbal means like words. So this is things that are like a description. So for instance, something that's like, a verbal description might be something like, Mr. Hopper has 30 Takis, comma, autocorrect, you are not helping me out right now. Quit doing that. Takis. How many people? No, that's not good. How many Takis? Please don't write this down, by the way. This is just me, like, giving an example. Let's drop us 30 Takis. How many would each person get? If there are 5 people. Okay, that's an example of a verbal description. And again, please don't write that down because it's a lot of writing unless you just really feel like you want to. So verbal descriptions, those are words, examples, and a problem. And then our last thing, expressions, those are like what we've already got. 2s, or maybe 4 plus x, or 2 minus y, right? Verbal or algebraic expressions. Give you a second to catch up if you have not already. All right, moving on to problem number 2 on the next page. The table below is what we call an input-output table. This just means whenever we take the input and put it into our expression, it gives us an answer we call an output. Kind of makes sense. Input is what you put in, output is what you get out. So question number 1, what pattern do you notice from the input to the output? What is happening to the input to make it become the output? So over here, we have some inputs, and they're becoming our output. So my question is, if my input is 1 and my output is 5, what am I doing to make that 1 become a 5? Well, it's getting bigger, so I'm either going to be adding or probably multiplying. In this case, to make 1 become 5, that would be times 5. Let me erase that. Times 5. But the thing about an input-output table, it has to work for all of them. So if I take 2 and I also multiply that times 5, will that give me 6? No, 2 times 5 is 10. So does times 5 work? No. This is actually not a multiplication one. So instead of 1 times 5, my other option is plus 4. Let's see. If I do 2 plus 4, does that give me 6? Yep. 3 plus 4, does that give me 7? Sure does. So what pattern do we notice from the input to the output? What is happening? So, oh no, come on. To make the input become the output, let me stretch this out. To make the input become the output, I add 4 to the input. So now let's go back and fill the rest of this in. 4 plus 4 would give me 8. Come on. 5 plus 4 would give me 9. All right, and then the next question, what would you predict to be the output if the input is 15? Well, we already said we add 4 to the input. That means I would take 15, add 4, and get 19. So my output equals 19. All right, question number 3. Draw what the output would be for each of the inputs in the table. Well, input equals 1 has 5. Input equals 2 has 6. Input equals 3 has 7. Input equals 4 means that would be 8. 1, 2, 3, 4, 5, 6, 7, 8. Input 5 would be 9. 1, 2, 3. I'm killing these triangles here. 6, 7, 8, 9. And for input equals 6, that would give me 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that 10? Yeah, that's 10. So I'm just drawing a picture. All right, our next part, our favorite thing. Describe how you can find the output for any input. So another sentence. To find the output. We've kind of already done this. To find the output, I add. How much do I add? 5 to 9 is plus 4. I add plus 4 to the input. And now my algebraic expression that I can use to find any output for any input. So I'm just going to put for input equals equals the letter I. And my expression, remember there's three things: a variable, a number, and an operation. My variable, got it, I. My number, I added 4. So my operation and my number, I, plus 4 is my expression. Alright, that will do it for tonight's lesson. It was a little bit shorter than normal. Hopefully that means that we will all be able to watch this video successfully and come ready to class the next day, ready to go. Have a good evening, and I'll see you guys tomorrow.